is Muhammad Hafiz bin Rizam. So today I will present about the question 2.0, that is large range interpolation polynomial. So first we combine the data with the three phase, that is rest phase with 2 minutes, exercise with 5 minutes, and recovery for 5 minutes. So this is the data, that is student A, Hafiz, and the student B, Hasif. So in the question, they have stated the missing data that is at the 105 seconds, and then we see the data. So we get that is the between 90 seconds and 120 seconds. So for the Hafiz, we have get the value 90 between 92, and then for the Hasif subject B is 93 between 96. So this is formula that we use to calculate the missing point. So we have the h function t, and t1 equal to 90 second, and t2 at the 120 second, and the t missing is 105 second. So this is how we calculate to get the h function at 105 for the subject A, that is Hafiz, where we use the 90 second will times with the 105 minus 120 divided by 90 minus 120, and then we plus with the 92 times 105 minus 90 and divide 120 minus 90, and then we will get the final answer 91 bit per minute. For the subject B, that is Hasif, we will get the function of 105, that is 93 times 105 minus 120 divided by 90 minus 120 plus 96 times 105 minus 90 divided by 120 minus 90, and then the final answer we will get 94.5 bit per minute. Hi, my name is Muhammad Asif Ahmad Sani, and my metric number is ID230015, and I'm going to present question 2.2. So for the first one is we going to calculate about 2 point forward and 2 point backward. For 2 point forward, we are going to use a formula like you guys can see, hn plus 1 minus hn over delta t. And for the 2 point backward, we are going to use hn minus 1 over delta t. So the delta t is 30 seconds. So now we are going to calculate the second point forward and second point backward for the first question. So there was a data that I take from 120 and 150. So for the subject A is Hafiz and subject B is Hasif. So the way we calculate is 120 minus 92 over 30, and we are going to get 0.93 bit per minute per second. So for the subject B, 126 minus 96 over 30, and we are going to get 1 bit per minute per second. So as you can see, this is the rate for the second point forward. And now we are going to calculate the backward. So the data I use is 510 and 540 for these two person. So for subject A, 92 minus 98 over 30, and we are going to get negative
0.20 beat per minute per second, and for the subject B is 92 minus 86 over 30, and we are going to get 0.20 beat per minute per second. So there was a difference for two people, as you guys can see as the result, the negative at for the subject A and for the positive at subject B. Let's move to the second question, the graph of rate versus time. So in this slide, show that the graph I using an Excel to make this graph by keying the data and insert the combo graph. So for the red line is for student A and the blue line is student B. So as you guys can see, the difference of the line for the red line and the blue line polar is not same. Let's move to the next question, number 3. So this question is about the maximum and the minimum rates. For there was two student, and for the first student is the max positive rate is 0.93, and for the student B is 1.00, and the most negative rate of student A is negative 0.20, and for the student B is negative 0.13. So let's move to the last question of 2.2, is compare the who has a heart rate response. So for based on the max positive rate is Asif have a higher maximum positive rate. So he has a faster heart rate response due to the maximum positive rate. So we can see the Hafiz has a highest most negative rate. So he has a faster recovery due to the negative rate.
For this part, we calculate the cardiovascular workload of subject Hafiz using the trapezoidal rule. The workload is defined as the integral of heart rate HT with respect to time. Since the data is recorded 30 seconds intervals, the step size is H equal to 30 seconds. Using the trapezoidal formula, the first and last heart rate values are 93 BPM and 88 BPM, giving sum of 181. The sum of all intermediate value is 2250. Substituting this into the formula, the total workload is 70,215 BPM per second. This represents the overall cardiovascular workload of Hafiz throughout the entire session. This slide shows the software validation for the trapezoidal rule calculation of subject Hafiz. The time and the heart rate data were entered into the FreeMath, and the trapezoidal integration function was applied. The computed result is 70,215 BPM per second, which matched the manual calculation shown earlier. This confirmed that trapezoidal rule was applied correctly and results are reliable. This slide shows the trapezoidal rule calculation for subject Hasif over the entire sessions. The heart rate data was recorded 30 seconds interval and substitute into the trapezoidal formula. Using the first and last values along with the sum of intermediate data points, the total cardiovascular workload is calculated as 69,660 BPM per second. This result will be compared with subject Hafiz in the following section. This slide shows the software validation of trapezoidal rule calculation for subject Hasif. The time and the heart rate data were entered into FreeMath, and the trapezoidal integration function was applied. The compute workload is 69,960 BPM per second, which matches the manual calculation shown earlier. This confirms the accuracy of the trapezoidal rule implementation. This slide shows the trapezoidal rule calculation for subject Hafiz during the exercise phase. Only the heart rate data recorded between 150 and 420 seconds is used with time step of 30 seconds. The first and the last heart rate values are 120 BPM and 96 BPM, while the sum of the intermediate values is 831. Substituting these values into the trapezoidal formula gives an exercise workload of 28,170 BPM per second. This slide shows the software validation for exercise phase of subject Hafiz. The exercise heart rate data from 150 and 420 seconds was entered into FreeMath and integrated using the trapezoidal rule. The compute exercise workload is 28,170 BPM per second, which match the manual calculation. This confirms the accuracy of the numerical integration for the exercise phase. This slide shows the trapezoidal rule calculation for subject Hasif during the exercise phase. The heart rate data recorded between 150 and 420 seconds is used with a 30-second time interval. The first and the last heart rate values are 126 BPM and 95 BPM, and the sum of the intermediate values is 830. Substituting these values into trapezoidal formula gives an exercise workload of 28,250 BPM per second. This slide presents the software validation for the exercise phase of subject Hasif. The exercise heart rate data from 150 to 420 seconds was entered into Freemat and integrated using the trapezoidal rule. The calculated exercise workload is 28,215 BPM per second, which matches the manual calculations. This confirms the accuracy of the numerical integration method. This slide shows the trapezoidal rule calculation for subject Hafiz during the recovery phase. Only the heart rate data recorded from 450 to 720 seconds is used with a 30-second time interval. The first and last heart rate values are 92 BPM and 88 BPM, while the sum of the intermediate values is 746. Substituting these values into trapezoidal formula gives a recovery workload of 25,080 BPM per second. This slide presents the software validation for the recovery phase of subject Hafiz. The recovery heart rate data was entered into the Freemat and integrated using the trapezoidal rule. The computed recovery workload is 25,080 BPM per second, which matches the manual calculation. This confirms the accuracy of the numerical integration for the recovery phase. This slide shows the trapezoidal rule calculation for subject Hasif during the recovery phase. The heart rate data recorded between 450 and 730 seconds is used with a 30-second time interval. The first and last heart rate values are 94 BPM and 89 BPM, while the sum of the intermediate values is 727. Substituting these values into the trapezoidal formula gives a recovery workload of 24,455 BPM per second. This slide presents the software validation for the recovery phase of subject Hasif. The recovery heart rate data was entered into Freemat and integrated using the trapezoidal rule. The computed recovery workload is 24,555 BPM per second, which matches the manual calculations. This confirms the accuracy of the numerical integration method. For the comparison, subject B shows a slightly higher cardiovascular workload during the exercise phase, indicating greater physiological demand during stair climbing. However, subject B also has a lower recovery workload, which suggests that his heart rate recovers more quickly after exercise. In contrast, subject A experienced lower workload during exercise but a slower recovery process. The integration results support the numerical differentiation analysis. The faster increase in a heart rate during exercise lead to a higher accumulated workload. Similarly, a faster decrease in heart rate during recovery results in a smaller recovery workload. Therefore, differentiation explains how fast the heart rate changes, while integration shows the overall cardiovascular effects during over time.